Hello and thank you for joining me again for some more reinforced concrete design. In this lecture, we will see how the principles of design and the assumptions that we've discussed previously come together to calculate a singly reinforced concrete section. Since the adopted model of a reinforced concrete section can be used in different ways, we'll start with the definitions of what design and analysis are. Design is the process used to calculate the area of reinforcement required to enable a given cross-section to resist the design moment. Design is usually applied to new structures. Analysis, on the other hand, is the procedure used to calculate the moment of resistance of a given section with known reinforcement and concrete properties. This is akin to an assessment and usually is applied to existing structures. As you can see, design and analysis are complementary engineering processes. Eurocode 2 defines the principles for design of reinforced concrete structures, which allow for certain variations in design procedures. As we previously discussed, the design of a singly reinforced concrete section for the ultimate limit state can be carried out using different stress-strain diagrams for concrete in compression, including parabolic-rectangular, bilinear, and rectangular diagrams. The application of a particular diagram in design will result in a corresponding distribution of stress in the compressed concrete. It should be noted, though, that the differences in stress distributions do result in insignificant differences in the final design. Here you can see the parabolic rectangular and rectangular distribution of stress. Throughout this course, we'll use the rectangular stress block. Let's consider a typical singly reinforced concrete section with a width of B. The bottom reinforcing steel is located at distance D from the top surface, where D is the effective depth of the section. Let's assume that the reinforcing steel has an area of AS and that the depth of the compression zone in concrete is X. The rectangular stress block method assumes that 80% of the concrete in the compression zone is stressed to the concrete compressive strength of FCD. Now we need to find the compression force generated in concrete and the tension force generated in steel. We know that compressed concrete is stressed to the level of its design strength. To find the compression force, we need to multiply the design stress, FCD in concrete, by the area in compression, which equals to 0.8 x times b. As we've established in previous lectures, the design compression strength in concrete equals to 0.567 FCK, where FCK is the characteristic compression strength of concrete. As a result, the compression force in concrete equals 0.453 times x times b times FCK. The tension force in steel equals the steel area AS times the design yielding strength of steel, which is characteristic yielding strength of steel FYK divided by the partial safety factor for steel gamma S. To maintain equilibrium in the section, the compression and tension forces should be parallel, opposite in direction, and equal. As a result, these two forces generate a force couple. The moment generated by this force couple is equal to the value of either force times the distance between the lines of actions of the forces Z, which is also called the lever arm. The position of tension force is known. As you can see, it is defined by D, the effective depth. The compression force is located in the middle of the rectangular stress block. As a result, it is positioned at 0.4x from the top of the section, and therefore the lever arm Z equals D minus 0.4x, or we can rearrange that into Z equals D, open brackets, 1 minus 0.4x divided by D. The moment generated by the force couple can now be found considering, for example, the expression for the lever arm and the compression force. This leads to the following expression for moment. This expression looks very complex and consists of many parameters. However, you should remember that it only represents the compression force in concrete times the distance between the compression and tension forces. Since the compression and tension forces were found from the maximum stresses that concrete and steel can carry, this moment represents the maximum moment that the section can carry. The only unknown in the expression for the moment really is x. And to find x, we start by introducing the parameter k. K is equal to the moment over FCK times B times D squared. The moment can then be represented as K times FCK times B times D squared. Substituting this expression into the expression for moment leads to this equality. Cancelling FCK times B times D square from both sides of the equality results in this expression, which after certain geometrical rearrangement gives the following quadratic expression for x. Hopefully we all remember how to solve quadratic equations, but the solution of this equation is as follows. Or in a simpler form, we can write it like this. This expression for x can be further rearranged into this, substituting the expression for x into z equals d brackets 1 minus 4x over d leads to the following expression for z, and considering that x is limited to 0.45d, it leads to the condition that z should be larger than 0.82d. The expression for the lever arm can be represented in different forms. Eurocode 2 limits z to the range between 0.82d and 0.95d. This condition assures that the designed concrete section is under-reinforced. If z falls under 0.82d, the section becomes over-reinforced, and if z rises above 0.95d, the section becomes lightly reinforced. It should also be noted that the condition that z equals or is larger than 0.82d corresponds to the condition that k is equal or under 0.168. The moment generated by the force couple can also be expressed considering the tension force in the reinforcing steel. This leads to the following expression for the moment. If the moment is known, the required area of steel AS can then be found as the following. Let's now demonstrate the application of the design equations with an example. For this example, we will consider a beam with a cross-section of 300 mm wide and 500 mm deep. The effective depth is given to us as 450 mm. The beam carries a moment of 120 kN, and the yielding strength of steel is given as 500 Newton per millimeter square, or megapascals. And the compression strength of concrete, FCK, is given as 25 megapascals. We need to design the beam reinforcement while assuming 15% redistribution of bending moments. We start off by calculating the parameter K. We substitute the values of all the parameters we've been given in the question, and we can find that K equals 0.079. And you can see here I then take that to the output column. For 15% redistribution, the limit value for K is 0.168, and the limit for the x to d ratio is 0.45. Now we can find the depth of the compression zone x using the following expression. X works out as equal to 85 mm, which is smaller than the limit of 0.45d. Now we can calculate the lever arm z using the following expression. If we introduce everything that we found until now, we will find that z equals 416 mm. Using the required parameters, we can find that the required area of the bottom steel, AS, is 663 mm square. So we need to provide 663 square millimeters of steel for the beam. As we already know, reinforcement is supplied as bars of certain diameters. In this table, you can see that the smallest manufactured diameter is 6 mm, the largest is 50. The limitation of bar diameters to the manufactured ones results in a difficulty to provide an exact amount of reinforcing steel. Therefore, in practice, we always need to provide a larger amount or an equal amount of steel to what we've calculated. To provide 663 square millimeters of steel, we need to select appropriate diameter and number of bars. This table gives the area of steel for manufactured diameters and bar numbers. As you can see, there are a lot of options that we can provide. We could give 1 bar of 32 millimeters, 2 bars of 25, 3 bars of 20, 4 bars of 16, and so on. The choice of bar diameter and number depends on the geometry of the cross-section and the requirements for cover and spacing between bars. For example, it could be difficult to position 4 bars with 16 mm diameter in a 300 mm wide cross-section. Provision of 1 bar with 32 mm diameters is not suitable as well, because 1 bar is usually only used in elements with no structural importance such as lintels. Therefore, the most suitable choices for us are 2 bars of 25 and 3 bars of 20. In this example, we will take 3 bars with a diameter of 20 mm and a steel area of 943 mm square. Now we need to check if the requirements for spacing between bars can be satisfied. First, we need to find the nominal cover to the reinforcement. That's the bar diameter plus 10 mm for deviation. So for a 20 bar diameter, the cover is around 30 mm. The spacing between bars is found as the width of the section, 300 mm, minus 2 covers, so 2 times the 30mm cover we just agreed on, and minus the 3 bars of 20. This gives us the total clear space between bars. We then need to divide this by 2, as between 3 bars there are 2 spaces. And as a result, the clear spacing between the bars is 90mm. And here we can see this all demonstrated in a cross-section of the reinforcement. The clear distance between bars should not be less than the maximum bar size, 20mm, or the maximum aggregate size plus 5mm. These limitations assure that there will be adequate flow of concrete around reinforcement during construction. Assuming a maximum aggregate size of 20mm, the clear distance between bars should not be less than 25. Therefore, the 45mm spacing we got in our example satisfies this requirement. When a parabolic rectangular distribution of stress in the concrete compression zone is adopted instead of the rectangular distribution we used, the derived expressions for moment, depth of neutral axis, and lever arm slightly change. Let's compare the expressions. These will be the expressions for moment, these will be the expressions for the depth of the compression zone, and these are the expressions for the lever arm. As you can see, the change of the stress distribution resulted in very small differences in the expressions. Given the condition imposed on the area of steel by the diameter of the manufactured bars, these differences will result in the same design. If you're interested in learning how the expressions for moment, depth of neutral axis, and lever arm were obtained from the parabolic rectangular distribution of stress, we can do a separate lecture on design using alternative methods. Eurocode 2 defines only principles of design, leaving decisions on the use of suitable methods and procedures to the engineer designing. Therefore, any legitimate way can be used for the derivation of necessary formulas. Design manuals have been developed by different engineering bodies, such as the ICE, the Institution for Civil Engineers, the IStructD, the Institution for Structural Engineers, the British Cement Association, the Concrete Centre, and concise Eurocodes, and so on. The manuals can be based on different methods and can use different symbols, but they'll all result in similar designs. Thank you for joining me in the design of a singly reinforced concrete section. I hope that was useful. Join me next time when we look at the assumptions made to create design charts and how to use them.